All right. Right now, I want to talk about this term called coefficient of restitution, and you've probably already seen the first video where they showed you some phenomenon having to do with coefficient of restitution. And the objective for this whole section here is to realize that even though we have this conservation of energy, and that energy is just transforming or changing the state that it's in, we don't always get the same height that a ball, whenever we drop a ball, we don't always get the same height out of the bounce. And then this is the reason why. You saw it in a video where you have, he explained sound waves and heat and those kinds of things, those kinds of energy transformations. But this coefficient of restitution tells us exactly how efficient our bounce is. And we will actually see this later on in a different chapter when we start talking about collisions. But right now I want to show you how to calculate this. So I have a ball, and if you can see in my diagram here, I drop the ball at this height, and it bounces off the ground, and then it comes back up, and that's as high as it goes before it comes back down. And so what I want to do is I want to come up with an equation to relate our coefficient of restitution. In the video, he explained that the coefficient of restitution, which is given by a lowercase e, equals the ratio of the two velocities. And so before and after the collision. So we'll call this velocity 2 and velocity 1. And then I'll go ahead and label those. Velocity 2 is right after the collision or right after the bounce, and that's velocity 2, and then velocity 1 will be the velocity right before the bounce, so velocity 1. Now it's really hard to measure our velocities at these locations because we have to have a special type of machine to measure velocity, and it's not something that's easily done. But it's quite easy to measure, well, where we drop the ball from and then how high it bounces. So if I look at this, I'm going to do some manipulating here with this equation right here, the V2 over V1, and I'm going to go ahead and continue to do proper math, and so you'll see some stuff that you might not agree with, but it will continue to work out, and then I'll get to an equation that actually simplifies how we can measure this coefficient of restitution. So if I look at this, velocity is a measurement that we can use to come up with kinetic energy. And kinetic energy is one of the things that we're discussing right now. So I'm going to go ahead and try and get this equation here into a kinetic energy form. So in order to do that, well, my velocities are squared in the kinetic energy. So I'm going to go ahead and square the top and the bottom. And I can do that. It's perfectly legal. And then what I'm going to do is I'm going to go ahead and multiply both top and bottom by 1/2 m. 1/2 mv2 squared all over 1/2 mv1 squared. Okay, because I squared the top and the bottom here, I actually need to square root that so that I'm actually taking it back to where it needs to be. So the square root of the top and the square root of the bottom, if I still divide those, it still comes out right. And then the same thing, the square root will come over here. Now there's some assumptions I need to make. I need to know that by conservation of energy, if I don't lose energy in this bounce or right after the bounce, then my PE final, which is given up here, has to equal my kinetic energy at the location 2. And so that's going to equal 1/2 mv2 squared. And then likewise on this side, because I'm dropping it, then I know that all of my initial potential energy at this location is going to turn into my kinetic energy down at this location. So PE initial equals KE1, which equals 1/2 mv1 squared. Now, I can actually take this, and if you see here, 1/2 mv1 squared is exactly what I have in that location. And then likewise, 1/2 mv2 squared is exactly what I have in that location. So if I were to rewrite this, I would rewrite it as E equals the square root of my final potential energy divided by my initial potential energy. But wait, there's more. I can actually simplify this even more. And so I'm going to erase this down here so I can use the space. And one thing I could note is that E equals the square root of Well, my final, or PE final, is going to be MGH. Oh, hit the wrong button. MGH final. And I know that my PE initial is going to be MGH initial. And I'll let square root. And if you notice here, then my M's will cancel and my G's will cancel, and I'm actually left with the coefficient of restitution equals the square root of my final height divided by my initial height. And that is much simpler to measure and calculate. And so the total of the last equation, I'll just rewrite it, is H final over H initial. And that's what we'll use in our labs. All right. Thank you. Okay, now I want to look at an example problem. And so if we were to look at this, and let's say I drop a marble from a height of, so H equals 0.65 meters. And let's say it bounces to a height of 0.45 meters. Well, I stated before that the coefficient of restitution is E equals the square root of my final height divided by my initial height. So all I have to do is I look at, I just fill in. All right, my final height is 0.45 meters, and my initial height is 0.65 meters, and then I do my math. So E equals, and then let me pull up the calculator. Set it right there. So I want to type this in. It's 0.45 divided by 0.65. Hit the equal sign and then square root that, and I get E equals, or my coefficient of restitution equals 0.8. Let's bring that back up so I can see. 83. And that's my answer. Simple. You're going to do a lab where you're going to measure your height that you drop a ball, and you're going to see how high it bounces, and then you're going to calculate this coefficient of restitution. Notice, meters over meters, they cancel, and so I have no units for my coefficient of restitution.